There we go. Okay, everybody. Hi. You already know who I am now. That's good. So I don't have to waste any time talking about what I do for a living. Very good. So the poor man's Haze test was inspired by, well, you need a scapegoat. So Tom, you're my scapegoat today. The worry about how silver degrades or any coatings degrade, and how do we start to understand from a quantitative point of view what is happening. So I started thinking about the poor man's reflectivity test, which uses a camera to measure the reflectivity. And I thought there's an opportunity here. I put it to the test at work and I got some very positive answers. And I said, okay, I'm going to try this, and it seems to work. So I'm going to talk about haze, what it is, where we get the blue haze from in silver coatings, how haze is measured per optical standards, and then the challenges with reflective optics. Haze is easily defined for transmissive stuff, lenses and glasses and windows and whatnot. When you get to mirrors, it gets a little different. Talk about the use of a reference white or a diffuse reflectance standard, which you have to make this work. Go through the process and go through the results. So, all right, so scatter and haze. There are two words that are used interchangeably, but they're not actually the same thing. Scatter is the physical process that light undergoes when it encounters particles upon which the photons scatter, and haze is the appearance of light where you don't want it. Okay, so it's the glow around the sun or the moon, the glow around stars, the clouds in the sky. Sorry, what? Oh, that's what's happening. Admit, thank you.
He works with us.
Better admit him. Yeah, okay. You'll hear brief interchanges as I'm reminded to admit people to the meeting. Okay, so scatter and haze are two different things. Scatter is the physical process. Haze is the appearance, the thing that you see as a result of the scattering. And you probably have heard of Rayleigh scattering. It's what causes the sky to be blue. I stole this chart off the internet, and I think it does a great job of explaining what the two types of scatter are. So you got Rayleigh scattering turning the sky blue, and that is because Rayleigh scattering happens when your particles are very, very small, like 1/10 of a wavelength or smaller in size. And because it's wavelength related, the effects are stronger for shorter wavelengths than they are for longer wavelengths. Kind of makes sense, right? And what you see here in this chart are antenna patterns that you get from a single photon scattering off of a single particle. And the probabilities are that, you get a lot of forward scatter, you get a lot of back scatter, and you get a lot of in-between scatter, but you kind of get a peanut shape out of it, right? And on the other hand, there's another kind of scatter called me scattering. And in that case, now you've got larger particles, and me scattering is quite a bit different. It comes about from things like fog, clouds, snow, etc., right? And it causes the clouds to look white. It causes snow to look white. And you can see on the antenna pattern for me scattering that is very forward directional. So a particle, a photon that hits a larger particle is going to tend to scatter more strongly in the forward direction than in any of the other directions. Now, to an observer looking up at the sky, you're looking at the Rayleigh scattering, again, more strongly affected. Blue light is more strongly affected than red light. The sky looks blue. If you're looking toward the source, that could be the full moon or the sun or whatever, you're going to see white, a white haze, a white halo around that source, right? You're all familiar with that. So there you go. Now, I kind of skipped over the thing on the left, but you can all read it. So it's the blue haze in silvered mirrors that we really wanted to address here, and that's where this is going. So let's go to the next slide, and that's a mouse wheel. Yep, okay.
You can also just push the
Page down?
page down.
Page down works. Oh, perfect, okay. Yeah. Oh, not the big 22. The question was the halo around the moon, me scattering. If you're thinking of the 22-degree halo, that big one, no, but just the one in close to the moon, that's me scattering. Yeah. Yeah. Okay. So let's talk about what happens on a silver coated mirror. So we have, first of all, a piece of glass. We've got silver crystals stacking up on top of it. We've got a telescope side and a bathroom side. I call it the bathroom side because that's how your bathroom mirrors are made, by depositing silver on the back of them and then painting them black on the other side to keep the silver from tarnishing. You didn't know that, Dan?
I'll never forget it.
You'll never forget it. Okay. All righty. Silver is very, very cheap to put down on large surfaces, which is why we're interested in using silver on our telescope mirrors of 25 inches and more aperture, because vacuum coatings just become astronomically expensive, right? So silver is a good thing, but we got to use the telescope side. We can't use the bathroom side. So what happens, as you can see in my cheesy diagram here, is that right up against the glass, you've got a great coating. But as these particles, they may be crystals, they may just be clumps of molecules, as they stack up, they become less well aligned. And if you continue spraying silver when your mirror is already done, you're only going to start adding haze. And we've seen this. Anybody who's done silvering has probably seen this, where you just overshoot and it's like, oh, now I got haze. What am I going to do about that? So part of the process is knowing when to stop at this layer and not go into this layer, right? So, all right, now.
You need an electron microscope for that.
Scanning electron microscope as you're spraying silver. Okay, let's see. So the deal is, of course, that when you have incident light coming down on something with a bunch of discontinuities in it, those discontinuities are scattering centers or scattering targets. And if they're very, very small, less than a tenth of a wavelength of light, as they should be, then you're going to scatter blue light more strongly because it's Rayleigh scattering. On the other side, you're coming in through glass and you're just seeing that nice surface of the glass and it looks great. So that it's all specular. There's really no scatter off the bathroom side. Okay, now I'm going to go way simple. I don't know everybody's experience. I know that there's some people who are going to glaze over as I talk about how light works, but for those of you who have never seen this before, this is for you. So blue light is of shorter wavelength than red light. We're talking about waves now. Light can be a particle or a wave, but a light thought of as a wave has electric fields that oscillate, and those peaks and valleys of the field are closer together in blue light than they are for red light. And that is the very property that causes the colors to look different, that causes dispersion in lenses and causes dispersion in diffraction gratings, et cetera, et cetera. So light is a wave of electromagnetic energy. Colors are dependent on wavelength. The shorter wavelengths are bluer. That's really all you need to know there. Now, refraction. You're very familiar with refraction, I hope. But if you're not, then you just look to the Pink Floyd album cover and it tells you everything you need to know. It tells you that light comes in to an angled surface. It bends and it bends, and the red light is bent less than the blue light. That is called dispersion. And
That's because of the speed of light change.
That's because the speed of light in the medium changes, as Dan Gray points out. That's right. And that's exactly where I'm going next. See, some of you are ahead here. All right, this is good. So the property that describes this is called refractive index. And the refractive index changes for different wavelengths of light. And that's what produces the dispersion. Air has an index of 1, water of 1.33, glass starts at about 1.5 and goes all the way to 2. Polymers like plastics are in the 1.5 to 1.6-ish range. And yeah, the higher the index, the more the bending. Okay, and artist, good work, but you really should have had the colors splitting at the beginning because they do. But okay, now here's the thing that you haven't thought of before maybe, and that's this. In the medium, the speed of light changes, as Dan pointed out, but because the speed of light changes, that means the wavelength has to change as well. So whatever wavelength you had in index of 1 becomes shortened in an index of 1.5. Speed of light goes down, the wavelength shortens accordingly. It's a conservation of energy thing, actually. Same is true for red. So now what was red light in air actually becomes blue light in the medium. You do the math, I had it on the previous page, or did I? No, I didn't. Maybe it's on the next page. Oh, no, it's right here. Wavelength in medium equals wavelength in air divided by the refractive index. Lead Andean. Okay, here we go. All right. So what that means when you think about scatter is that if I have a coating over this silver of a refractive index greater than 1, the light that comes into that material has a wavelength that is shortened. It now scatters what was maybe red light, now becomes blue light. It Rayleigh scatters and then comes back out. It comes back out as blue light again. Or
is passing through it and then back out again double the index, or does it not matter at all?
no, passing twice through the medium, what happens is this. I kind of glossed over it. I should have said, don't worry, it shifts to red again after leaving the medium and all as well. So if your red light becomes blue light in the medium, reflects off the back, comes back out to here and goes index of 1, it's now back to its original wavelength. And that's important to understand. There are no permanent effects here. Okay. So this is what happens when your mirror is wet. You've sprayed your silver, everything's wet, and you look at it and it's, oh, it's got blue haze all over it. And then you let it dry and it's like, oh, it doesn't look so bad. Somebody needs to mute. I will mute you if I find you. Oh, mute. Not working.
Good gracious. Hey, Andy.
Andy, mute. Mute, Andy. He's not even there is the problem. He doesn't know he's making noise. And, I've obviously bored him to death, so he's like, I'm going to play drums over you.
Okay.
I think I can kick him out. He's in there twice.
Oh, very good. Thank
All
you.
right. Okay. Wow.
Thank you, Andy.
It was very entertaining. Where was I?
Okay, so light waves return to the original wavelength.
Light waves return to their original wavelength in air when they re-encounter air. If that wasn't the case, then all hell would break loose and, well, there would be something wrong with the universe. Okay. So as I was saying, you've sprayed your silver and it by gosh, looks like you might have some blue haze. And if you let it dry, it goes away or it reduces anyway. And this is why, is because now you're back to in air and you've got red light doing red light things and blue light doing blue light things. Okay, let's move on. It's going to let me, or mine all, there we go. Okay, this is really just kind of a throwaway slide. I put this in here for anybody who wants to learn more about Rayleigh scattering. I looked at these 3 links and boy, in 2 minutes, I learned everything I needed to learn about Rayleigh scattering. Of course, I already knew from before, but it was good. It was good. And so you can go to these links and get up to speed here. So, all right. Now, I'm going to talk about how haze is measured professionally. I've done a lot of this myself. You use what's called an integrating sphere. It is a ball on the inside of which is coated typically barium sulfate, but there's some other proprietary polymeric stuff that lasts longer, and it's very highly reflective, like 98, 99% white reflectance and very diffuse. So question about previous slide. Yes.
So, oh no, before that.
Before that.
So red light comes in, turns to blue and scatters.
Yeah.
And leaves and comes back.
Yeah.
You still see haze.
Yeah.
Because it was blue when it hit the circle.
Right. So
it won't be, oh, okay.
So the question was, light comes in red, shifts blue, scatters off the silver, comes back out of the water and shifts red again. Do you still see haze? And the answer is yes. The thing is that, I guess what I should really say is that when your mirror is wet and you see this blue haze, it's not pure blue. It's kind of bluish white. It's more blue than it is red, but it's kind of a bluish white. It means that all wavelengths are being scattered. That means red light coming in to that mirror is being scattered, and when it comes back out of that water, it's still red light, and it has been scattered. When the mirror is dry now, the propensity of that red light to scatter is greatly reduced. And in fact, the propensity for all light to be scattered is greatly reduced. So that's why a dry mirror looks better than a wet mirror does. Does that answer your question?
Except for the fact I'm wondering, you were distinguishing between red and blue light when you talked about Rayleigh scattering for white sky.
Okay, except for the fact that I said Rayleigh scattering is what makes the sky look blue.
Right.
But is the sky as blue as that blue tablecloth? No. Maybe if you're very lucky, but it's not pure blue. The sky, in fact, looking out the window right now, the sky is kind of blue, but it's heavily affected by smoke, which is adding in Rayleigh scatter. I mean, it's adding in me scatter. The sky is never a pure blue. It's sky blue, right? It's kind of a muted blue. All wavelengths are being scattered, blue more so. So you got to think of this in terms of probabilities, not absolutes.
So is the scattering by the mirror less blue than
Scattering by a mirror less blue than the sky? I'd have to think about that. I would say that if you screw it up, your scattering is going to look white. Your mirror is going to look white if you screw it up. If you get it right, there's going to be so little scatter that that's a hard question to answer. Maybe less blue, maybe more blue, but so low that you just can't see it. I don't know. There's a slide on this, sort of on this later. I'm going to compare. I'll give it away a little bit. I'm going to compare a really good professionally done aluminum coating, a really crummy silver coating, and a pretty good silver coating. And you'll see some differences going on in the numbers, okay? So hold that thought. Let's move on to how haze is measured. So ASTM D1003 is a standard that one would follow to measure haze in a window or a lens, something transmissive. And you put your sample where that yellow box is shown, but you got to take two other measurements to kind of calibrate the system. And the math is very simple. It's the value you measure at T4 divided by the value you measure at T2 minus the value, the ratio of T3 to T1, okay? And times 100%. And when you get to values of about 1% or lower, then you know you're in the good range. And if you see values that are like 0.1% and lower, then you have not only a good optic, but a really good measurement system, because it's hard to get down to these kinds of measurement numbers. I typically see, with this kind of a setup, about 0.05 to 0.1% just in this coefficient here, T3 divided by T1. And then when I put the sample in, depending on what it is, it could be anywhere from, you know, another 0.2% to several percent, depending on what it is I'm measuring and how it was made. So
So it looks to me like T3 would have 0 on the.
the question was, looks like T3 would have 0 on the detector. And the answer is, you're right, if you had a perfect beam of light going through here. And I typically use a laser, which is as damn close to perfect as you can get. But in a good dark room with a good sensor right here, you pick up some stray photons. And they show up down in the picowatt or nanowatt range when you've got milliwatts of laser light coming through. So it depends on just how clean your optics. If you're measuring something that's really stinking clean, you're going to need this value to be really good, and you have to measure it. So this is the standard. All right. Now, this is not what I'm going to impose on the amateur astronomy world, because it wouldn't be a poor man's Haze test otherwise. But before I show you what I'm up to, what we got to know is what happens with reflective optics. So there's another set of standards, ISO 13803:2014. This standard talks about paints and varnishes, and it's kind of a combination of gloss testing and haze testing as well. Like you're looking for, is my paint glossy or is it matte? Is it flat, eggshell, whatever the heck, you know, you get at the paint store, right? And the way they set this test up is that you have a light source. You shine that incident light on at about a 20-degree angle on your paint surface, and you get a combination of diffuse reflection and gloss reflection, and it all lands on your diode array. Okay, what they're not showing is that you probably have a camera here instead of just a diode array, but okay. It's what you get when you steal from the internet. So it also requires the use of a reflectance standard. And I'm going to show you that coming up here. But the geometry of this thing is real simple. The concepts behind it are real simple. And again, thinking about what the PMRT, the reflectivity test, looks like, I realized that I probably have the tools at my disposal to do something like this and actually get to an accurate haze reading. So let's see. Apparently, I just skipped to what my reference white is. So it's a chip of Teflon. In fact, I have it for the people in the room. It's sitting on the table over there under a desk lamp. So I measured my Teflon chip against a reflectance standard at work with a calibrated photometer. And the results that I got were that my Teflon was about 86, 87, 88% reflective in the 3 color bands of interest. So Teflon is really not a very good reflectance standard, but I like it because it's easy to keep clean. Honestly, printer paper is typically 90 to 92, and you could do a better job with printer paper, but I thought, well, Teflon, okay. Point being, I think you'd be in good shape if you just went to Office Depot and bought a ream of 92% printer paper and then laid down, 10 sheets of it on top of your mirror as the reflectance standard. That would probably work just fine. So, all right. So now I'm going to talk about the process, how it's set up, what the measurements look like, and then I'm going to get to the results. And this is very much like the ISO 13803 standard, but I do something fundamentally different here. Where in the standard, they had the measuring camera in the specular beam. I put the measuring camera out of the specular beam so that I only look at the haze. And that was the key. That's all I needed to do. So the setup is simply this. If you're in the room, you can see it right over there. You have a spotlight shining on a mirror with a reflectance standard sitting in the middle of it, and then something black up above. And I tried this both with a sheet of black EVA foam over the top of my telescope right here. And then I decided to try it outside at night under a light polluted sky. this spotlight being so bright that it completely swamps whatever the sky is doing. And I got a good black in the night sky. So this becomes very easy for people to do now. You don't even need a piece of black foam, but you do need to have a spotlight, a reflectance standard, and a measuring camera. And the measuring camera that I'm using at the moment is my Google Pixel 4 in RAW mode. And the RAW mode is important, just like it was in the PMRT. Okay. Now, what's happening, of course, is that you're going to take a picture of this whole thing, and you're going to see what's called Lambertian antenna pattern coming off of your reflectance standard. So you want something that's a good flat white, a sheet of printer paper, piece of Teflon that's been fine sanded, and that's going to give you your reference. And then coming off of the mirror, you see I moved my ray of light over to the mirror side, and now you're going to have a little bit of antenna pattern from a Lambertian, a little bit of antenna pattern from me scattering if you've got large particles, and then a specular beam that's going to miss your camera. And your camera is now only looking at the scattered light. Okay. So you're looking at these lobes from me and Rayleigh scattering only. All right. So what does it look like? Well, here's the first step. You record your image in RAW mode, and I just cut and pasted the image J appearance of that raw image, and it looks terrible. You can barely see the mirror. The reflective standard is dull. There's a big glint off of whatever was behind the mirror, and but that's how it gets pulled in. And you want to make sure, of course, that your white reference right here is not overexposed. You hit 50 to 70%, you're good. If you overexpose, you're going to have bad data. The silver itself is going to be black. You're not going to see the mirror at all, hopefully. All right, you're going to calibrate the camera. So this is where I hold this chip of Teflon up against the sky. I put it on a post and just kind of held it at arm's length, and then shot it with my cell phone in RAW mode, using the sky as the background. And I'm going to come back to this image later and show you how I used it as a measurement tool. Okay. All right. And now we get into the real nitty gritty here using image J. You open up the brightness and contrast tool, and it pops up with a window. It's called B&C for brightness and contrast. And if you pay attention to the slider at the bottom of your image, you can slide from red to green to blue channel, and this window will update accordingly. What I did here was I just pasted it in 3 instances, but you never get 4 windows here. You only get the one, and you have to pay attention to what color channel you're in. Luckily, what they do is the little histogram here is color coded. So it's red here, it's green here, and it's blue here. So the first thing that you do is you slide the maximum down, and it brightens up the red channel. And then you go to the green channel and you slide the maximum down, and you keep doing that for the blue channel. And now you get to where you can actually see your mirror against the background. But this is important. Do not hit apply. Do not hit apply. You're not going to change any of your histograms. You're just changing how it's being viewed so that you can take some accurate measurements. All right. Then what you do is you grab one of these tools. So you get the polygon tool, and you can create a closed form around the inside perimeter of your mirror. And then you want to exclude the reference. So I have to cut in a channel here, and you can see it enlarged here. And then you add that to your region of interest manager. Then you go and create a polygon on your reference itself and add that. And now you've got 2 different regions of interest. They're mutually exclusive, and one's looking at only haze, and the other one's only looking at the reflectance standard itself. At this point, it looks just like the PMRT. You've got 2 places to measure. You go down here to more, and poor man's reflectivity test. Okay. So then this, if you've ever done the PMRT, this will look very familiar, because you'll have your 3 regions of interest, you get 2 regions of interest. That's area 1 and area 2, and your 3 color channels. Copy and paste. I like to put it in Excel. We only care about the mean values here. So I look at mean 1 and mean 2, which you see here, mean 1 and mean 2. And then channel 1 is red, channel 2 is green, and channel 3 is blue. So I have it red, green, blue here. Then you do a little bit of math. And the math is pretty straightforward. So, oh wait, I got to talk about the calibration image, right? Okay, so this is that calibration image that I took of the Teflon up against the sky. I do the same thing. I created regions on either side, and then one right on the Teflon itself, and then I did the math. And so what I'm doing here is actually measuring the haze in the camera itself, because what if my lenses are dirty in my camera, right? Well, obviously I want them to be as clean as possible, but they'll never be zero. So, and lo and behold, I got a stronger value for haze in the blue channel than I did in the green or the red. And my camera has its own blue haze, but there's fractions of a percent here, which is great. That's what I would expect to get for a good camera. 0.2, 0.1%, no problem. Question, yes. Oh, admit, yes. Thank you, okay. So I kind of think that these low values is that haze, or is it just noise because it's a cell phone camera? But we can debate that. In the end, it's not very important with respect to the kinds of haze that we're seeing in actual mirrors. All right, now, the final answer then is to do the same kind of math on your Teflon and mirror. And so mean 1 was the Teflon, mean 2 was the mirror. And well, the math is simply this: mean 2 divided by mean 1 times the absolute reflectivity of Teflon, which you recall was in the 80s, right? So that scales things, minus the camera haze. So that's why you want to know what the camera is. So you get that to take off. All right. So there you go. After having a piece of silver sitting in my garage for 3 months, I got a haze level that was on par with my expectations. It was never a perfect mirror. It's sitting right there. It has extra dust on it now than when I took the data back in early September. But these are the comparisons now of 3 different mirrors in different states. So over here on the left is a large secondary mirror that's going to be put into my 16-inch if I ever get it done. It's a brand new coating. This is Agena Optics that I got it from. So it's not enhanced silver, but darn good and clean. What you can see right up here is the lamp itself. That's the very same lamp that's on the table here. And I let it creep into the view so that my camera's exposure would get this right. So that, you know, this is overexposed, but this isn't. So that was kind of a nice trick. And it also kind of gives you a no kidding scale of just what this mirror looks like. Like I said, it's brand new. You can see some flaws on it. I've got dust on it, by golly, you know. So there's something going on, but it's a really good mirror. This is my current 12-inch mirror. It looks terrible, but it gives me perfectly satisfactory views. It doesn't pass the flashlight test, but I'm very happy with the views. Yeah, I want to recoat it very soon. And this is this 11-inch thing. It's a spherical mirror, not a telescope mirror. And when it was freshly silvered, it looked extremely good. And these are the numbers on it. So here we see this new diagonal came in with numbers that were, you know, 0.25% and lower. And they didn't really follow expectations for Rayleigh scattering. The green was a little higher than the blue, for example. Well, why is that? That could be the camera calibration. That could be just the fact that it's so dang good. My horrible looking mirror here was only 1.5% or so, stronger in the blue, of course. And this more of a fresh silver here was 1.2, 1.15, and 0.83. And this followed the blue haze thing very nicely. More scatter in the blue and less in the red. And a perfectly serviceable coating, by the way. The flaws that you see in here are actually scratches in the glass. They're not silver flaws at all, except for this big sucker right here, which was a thumbprint or something I didn't get cleaned off and the silver didn't stick.
Well,
No.
you should be able to tell who put the thumbprint on there by analyzing the print.
That was Dan with a snarky question. All right. Now, so then that leads me to my last slide, which is going to segue into life testing, and then we're going to have some discussion. But before I get there, what does Midas do to this whole thing? Midas is a coating that we put on our silver mirrors to keep them from tarnishing. And the whole reason I had the introductory stuff about wavelength in a medium changing was not just to explain that your wet mirror looks more hazy than a dry mirror, but what about the Midas? Because that's a transparent film overlaying the silver and it's doing the same thing. I don't know what the refractive index is, but it's not 1. It's got to be somewhere around 1.5 or higher, who knows? And so, well, what I did was I poured Midas in the center of this mirror and let that sit for 10 minutes. And then I quickly drained and rinsed it off. And so I have a central Midas zone and an outer periphery that's bare silver. And you can see that, lo and behold, the Midas area has slightly more haze than the silvered area. The previous measurement was averaging everything. And now this separates them out. And you see, lo and behold, the silver is a little less than the average and the Midas is a little higher than the average. Both follow that Rayleigh scattering assumption quite well. And so, yeah, the Midas is adding a little bit of haze to the system. Is it worth it? Well, that's a personal choice, but the data says, by golly, it sure is. So this is the same mirror. The date it was coded was June 5th of this year. Central part again with Midas. And I had then did the PMRT at various times up to, what was that, August, I don't know, 6th or 7th, something like that. And you can see that the silver, the bare silver is degrading much more rapidly than the Midas silver is. And this is completely unprotected in the garage. I keep it nearly vertical to keep dust from collecting on it. But other than that, you know, it's seeing everything. And it's no surprise that it's tarnishing now at basically an equivalent rate. But in the early days, obviously the Midas was doing something. And so therefore, you know, use it. We have some evidence now of mirrors going out from 1 to 3 years if properly stored and used. So this is a good thing. And at this point, then we can have an open discussion on silver coatings. Questions about my presentation first, please, and then just whatever anybody has to say about it, your results, experiences, learnings, whatever, we'd like to hear it. And I think, how long do we have, Howard?
We have about 8 minutes.
8 minutes. I went longer than I thought. Okay. All right. Questions? Yeah.
I was speaking to Howard the other day that silver tarnishes, that tarnish affects blue light more than red light. Did you see that?
Yeah. So does tarnish affect blue light more than red light? Yes, absolutely. That was reported on earlier. As silver tarnishes, the absorption coefficient goes up more quickly in the blue than it does in the red. Absolutely. And the tarnish becomes yellow. Yes.
Is there also an effect with the anti-tarnish? That was just the graph that you showed us.
Yeah. So what I'm doing in that graph, what are you seeing? This is actually the blue channel reflectivity. Yes. The red and the green are flatter. So I'm going for the worst here. What I think we've shown before was that once your blue channel drops to below 90%, it's generally time to think about recoding. And when I say 1 to 3 years, I'm talking about blue channels that have gotten into the high 80s by the time they're recoded.
Yeah, and I think that's very true in terms of just the visual aspect, looking at the coating,
Mhm.
looks like, oh God, this looks horrible. I need to recoat it. On my, the longest I went with the silver coating on my 28-inch was 2 years, 23 and a half months. And by far the best, most detailed, most brightest, most emotionally satisfying views of the Veil Nebula complex were just a few weeks before I took that measurement. And in the blue, I was at 88%.
Wow.
Yeah,
After 2 years.
after 2 years, yeah. Yeah, I was still well into the 90s in the green and in the red channels. So even an ugly looking silver coating, just by glancing at it, still performs or can perform wonderfully well.
Right.
If an aluminum coating looked that bad, as my almost 2-year-old silver coating did, I would be up in arms.
Yeah. Yeah.
Because of all the money I would.
It's an expensive coating in
But
aluminum.
the
Yeah.
thing of it was is that it performed so beautifully. And yeah, it's pretty remarkable because we can measure this so easily now because of your PMRT. It's really a valuable tool to help gauge, do I really need to recoat my silver coated mirror to get better performance? That is significantly noticeable.
Right. Well, and as they say, beauty is in the eye of the beholder,
Yes.
and that's a major factor in visual observing. I'm very encouraged to hear you say that. And my problem has been not tarnish, but all these other things that have
Yes.
gotten on my mirror.
Oh,
And
yeah.
that's because of how I store it. And I need to up my game on mirror storage. You've got that dialed in, Howard, I think.
Well, I think Mel has it dialed in just because he
Oh,
lives in
Well, okay. No,
Central Oregon.
Mel doesn't count. All right. I'm sorry, Mel, but
We all moved to Sisters, would be in better shape.
yeah, we would.
Midas coating interfere with removing it chemically?
No, Midas just doesn't harm. It has no protection against green river or ferric chloride. It just comes right off. Yeah,
Some of the coatings they put on the aluminizer.
absolutely. If you were to put silicon dioxide over silver, then your removal time would increase, but you would still be able to remove it. Yeah, yeah. Any questions online? I'm going to look in the
Rob,
chat.
I put one in the chat for you.
Oh, very good. Flashlight tests. Have you done the test, separated the results between passing and failing flashlight tests? Well, so I don't really know what it means to pass or fail a flashlight test, but I do know what these various Haze values look like. So I think that's a question to dive into in the future as we get more familiar with end of life of coatings and performance and all that.
So I can see where Mel's coming from in his question, because when he first silvered his 30-inch mirror last, I guess December it was. And I mean, it turned out, it was the best silver coating I've seen so far. And we as soon as it was moderately dry, we put it in his telescope and wheeled it outside to observe. And during all that, I shone my red flashlight down the optical tube just to do the flashlight test. And I could see the reflection of the red flashlight, and there was no visible scatter. There was no dust. There was no anything.
Mhm.
It was just this deep well.
Yeah. Well, you're
And-
using a red flashlight.
yeah.
Good.
So
but
that's good.
yeah.
And then I turned on the white flashlight, and the same
Oh.
thing. I mean, it's like there was nothing there.
okay.
I mean, and I
Yeah.
imagine that, if a Haze measurement had been done on it right then,
Yeah,
it would have been an extraordinarily low score.
that probably would have been on the order of the camera itself.
Yeah.
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 And I'm not surprised. I mean, I am surprised that a 30-inch mirror can be that good everywhere with not a single flaw. That's truly remarkable. When I first put a polish on my 16, I did silver it and reported on that. I think that was some time ago. Remember the mirror kissing?
Yes.
That, of course, I never put it in a telescope, but I I couldn't see any flaws in that either. I'd achieved a very good state of polish. So unfortunately, you know, it wasn't parabolized. So who
Yeah.
knows what I'm going to get when I'm done.
Yeah, I think maybe one thing to add as a color, as an addition to this discussion is that, you know, a silver coating, when it's done really well, I think probably has less scatter than an aluminum coating done really well. Because I've
Well,
never
yeah.
seen as good a flashlight test on an aluminum
okay.
coating as I did on Mel's 30.
That could be true. I don't know, but it's certainly worth putting to the test. I thought that secondary of mine was as good as any coating I've ever seen, but
But,
it
you
was
know,
aluminum.
Yeah, it's aluminum versus silver,
Yep.
and maybe there's something
Maybe.
different between those two.
Yeah, yeah. I know my 12-inch isn't polished out all the way, so it'll never have a good low answer. But well, someday it will.
Yeah, someday.
But not soon. Question.
I've seen the
Is there?
you're measuring the haze, so what is not actually functional.
Yep.
Does that mean that 1 minus the difficulty is actually two complementary?
Yeah.
And
So
then why
yeah.
you should use the reflective test rather than a haze test? Are they?
they're different things. So the question was, what is that energy, the Haze energy, where does that fit into the conservation of energy? And then should I use one test or the other? And the first answer is you got the sum total of light hitting your mirror. You've got reflection, transmission, absorption, and scatter. And typically in optics, we treat it as the sum of the reflection, the transmission, and the losses equals 1. Losses are then absorption, scatter, and whatever other things that might be taking your photons away from you. So energy is conserved, obviously. Now, should I use one test or the other? The answer is use both. The reflectivity test was developed to get a handle on how silver was aging, so we could see what the tarnishing was doing. The Haze test came about when we realized that sometimes this blue haze is a problem where it isn't, right when you coat the mirror. So right when your coating is fresh, if you were to do this test and see that you're getting numbers in the 1.5% to 3%, something like that, I'd question it. And I'd say, maybe I want to recoat that because I got all my chemicals ready to go and see if I can't do it better. And if not, then just use it and see what you get. But it wasn't so much meant as a life test or is my mirror too dirty test. That I think is more of the beauty is in the eye of the beholder category. But for those who have to know, and I'm certainly one of those guys, you know, how good is silver compared to aluminum? Ideally on the same substrate would be great. This would be a cheap way of finding out. So
if you measured a value for haze on them
mhm,
that was high,
mhm,
let's say it's like 4 or 5%.
yeah.
Okay, so it's really a high number. Would that impact the reflectivity score?
Yes, so the question was, would a high Haze value impact the reflectivity score? Well, it has to because of conservation of energy. So if I had 5% in Haze, I would expect to not even come close to 95% in the reflectivity because I know I've got some absorption there. So that's another.
Plus it would be just readily visible to the naked eye.
Right, it would just look like a cloudy mirror at 5%. Absolutely would. Yeah. How am I doing for time?
Depends on-
Time's up. Okay.
Can I ask a question?
Sure. Yeah, go ahead.
So going back to your stacked bricks image, you know, of the silver coating, how are we going to eliminate the haze or at least dramatically reduce it? You know, because you said basically, you know, if we're laying down more silver on top of silver, that's when we get into trouble. You know, and you know, I seem to be like when I'm coating it and I look at it from behind and I can see through it, I just intuitively feel like I don't have enough silver, and so I want to lay down some more. So how are we going to find this sweet spot of the right amount of silver to get the reflectivity that we want without inducing haze?
Thank you, Tom. In fact, I really kept you in mind as I was preparing this thing, because you have shown us some really good silver coatings. And what I think is the following. First of all, these coatings are so thin that they'll never become completely opaque before they become completely hazy, right? We're getting numbers that are in the 90s, 95 to 96-ish. I think that the other 4% is really transmission losses more than it is absorption losses at these thicknesses. So I kind of think we're there on the thickness of the coating, and it really is all about knowing when to stop spraying. When you get that, you look through the silver and you see it's a dark blue and it's uniform, stop. And at that point, do a PMRT on it, and your numbers are in the 90s, man, you did great, right? If it's not uniform, keep going. If it starts to become hazy, stop and do both a PMRT and a PMHT on it and see what the numbers are before you decide to do anything aggressive like buffing it or whatever, right? That's my recommendation. And I think there's still a lot to learn. So, and Tom, I know you're going to push the envelope on this, and I'm rooting for you. So that help, Tom?
Yeah, no, definitely. So I guess I need to be more patient on my next one, and I'm running out of my original chemicals, so I'm gonna have to be using the new stuff, which is just inherently slower. But I guess I'm just gonna have to hold back a little bit and maybe stop before I think I should, but do the measurement. And unfortunately, once you do the measurement, it's too late, and you're gonna have to like strip and redo the whole process. So yeah, but yeah, I guess in the next one I'll try that. I'll err on the side of less silver and maybe be pleasantly surprised by the reflection number still.
Yeah.
Okay, thanks.
I would, my recommendation to you, Tom, is make sure you have a uniform coating as you look through the mirror, and that when you get that uniformity, you're probably done. And I think you'll have very good results with that. All right.
Yeah, I noticed though that, because when the mirror is on an angle, that inherently it seems like it's less coated towards the top of the mirror than along the bottom of the mirror. So, I tend to do a coat. Yeah, right? Well, that's what I tend to do. Yeah.
That's a good technique. I've learned from you on that one. Howard?
Yeah. No, that is a good technique.
Okay.
So I just want to add to, so this is about blue haze.
Well,
sometimes we see a whitish haze.
Yeah.
And that's a whole different thing. I think that's I'm starting to think that's the result of a cleaning process that we didn't completely rinse everything off.
Yes. That white haze can look like you spilled white paint on it even, or sometimes it even goes brown. And then you've got cleaning problems and chemistry problems. And
when it's brown, it's chemistry.
Yep.
But when it's a white haze and it's kind of splotchy looking, I think that's just incomplete cleaning.
Yeah, I agree.
Or at least rinsing.
Yeah, I totally agree. In fact, when I started using the chalk for cleaning, I thought I was clean, and I was getting the haziest coatings I'd ever gotten. And then I realized, I should probably just use a clean glove and wipe the whole surface and rinse and wipe and rinse. And it was your finding on Mel's scope, I think, about that with the
because
stripe
on his first attempt, it was just like white haze everywhere.
Yeah,
and you could see where the white marks were.
Right.
So it was like, obviously we just didn't clean it well enough, didn't rinse it well enough. So the second time around, Mel was fastidious in making sure. And the key there was then on his second attempt, when he was rinsing and making sure everything's clean, the glass was squeaking.